Sorry. And so we talk about chromatography in terms of the number of plates, the number of these little separations that we can do before we start that condensing process, right? That receiving process. And so in chromatography, we talk about theoretical plates, right? Because there's not actually physical plates in our HPLC column. But we have these sort of theoretical plates, and these theoretical plates really mean nothing to us, except that the more we have, the better our separation is, right? And so an increased number of plates means increased separation. And usually that's a good thing. And usually we want good separation in our different compounds. Okay. Theoretical plates is also a very even so this this column here also has plates, right? But let's say that you know, one compound reflux is at this level, and another compound reflux is here, and another compound reflux is here, and another compound reflux is here, and another compound reflux is there, right? The plates are not necessarily all equal height in real life if we don't actually have plates, right? In a distillation column, you have 1, 2, 3, 4 plates. There are 4 plates, period. They're 6 inches apart, whatever. In theoretical plates, each theoretical plate is in a different location because it just depends on what you're running. And if you change mixtures, that same column might have a different number of theoretical plates, right? It might have a different, those theoretical plates might be in different positions. And so this idea of theoretical plates is different for each system. Right? Even a single sample, you know, even the same column, if I have the same HPLC instrument and I run one sample on it versus another sample on it, those samples are going to come off with different theoretical plates because they interact with the column differently. So what this leads us to is this idea of some sort of equilibrium, right? If we are going toward this idea of, okay, at this point in our column, there's something that really doesn't go much above that, right? So he must be in some kind of equilibrium where that's as far up the column as he goes, right? He's not going to go up there unless we give him more kinetic energy and a little more heat, and he's going to climb up the column a little bit more, right? And so we have to increase the heat if we're going to push these things out of our distillation column. And so this distribution equilibrium, KD, is this ratio between the concentration of our analyte, I'll do like this, in the mobile phase, divided by the concentration of our analyte in the stationary phase. Oops, I'm sorry, I got that backwards. It's, remember, oopsie. Remember, it should be products over reactants. And if we start in the mobile phase, we end in the stationary phase. And so this is our distribution equilibrium. Each analyte is going to have a different KD value, and each column is going to give us a different set of KD values. And so, you know, knowing like a certain KD value is somewhat useful, but really because it's going to be different for every different instrument, every different column, and even if you have, you know, the same analyte but in a different solution, it's going to be slightly different. And so KD is a useful thing for us to think about, but once we start getting into some complex mixtures and talking about HPLC, we're going to shift from KD to a different coefficient, a different way of measuring it. And so again, a very broad view here. One of the easiest separations that we do is in a separatory funnel. Right? We have our two phases. In this case, it's not a mobile and a stationary, right? These are both liquid phases, so we call this a liquid-liquid extraction. But we still have that distribution constant. Again, the ratio of that constant depends on where we're going and where we came from. But if we think about it as being the concentration of C, well, let me use A. If we're talking about A in the aqueous phase, setting up an equilibrium with A in the organic phase, right? Then we get our KD to be the concentration of A in the organic phase divided by the concentration of A in the aqueous phase. Another way to think about it, you know, if we're doing liquid-liquid extraction. There's another quantity that we can take into account because all these concentrations depend on the volume. And so if the volume of the organic solvent is very different from the volume of water or whatever, there's a capacity factor that we can plug in. So the capacity factor tells us something about the volume. And that's just a K sub CF. And this is equal to KD times the volume of the organic layer divided by the volume of the aqueous layer. And again, if we were going from the organic into the aqueous, we could reverse these two. It all depends on what your equilibrium is. And so the reason we use this is because unlike in a stationary phase, in a mobile phase, stationary phase situation, when we talk about two liquids, as long as it's water and hexane, for example, that KD is going to be pretty constant for that particular analyte. Right? And so the KD might be very well known, but if we're using different volumes, that's got to adjust a little bit because the concentrations change. And so this capacity factor lets us use a looked up KD with whatever volumes we have, and then use that capacity factor to give us some information about that separation. Both of these things tell us something about separation efficiency. If we're going into the organic phase, but our volume of organic solvent is very small, are we going to be able to push a lot into the organic phase? Not at all, right? If the volume of our organic phase is 10 times out of our aqueous phase, we're going to be able to push a whole heck of a lot of stuff into the organic, right? And so this capacity factor tells us something about how efficient our separation will be. And so let's do a little example, a liquid-liquid kind of example. We've got caffeine in a 100 milliliter cup of coffee, right? That's a pretty small cup of coffee. Right? That's like an Italian espresso or something. And we're using 250 milliliters of chloroform to extract it. We want to know how much caffeine is going to be in our chloroform layer. And it gives us KD. It gives us that separation coefficient, that distribution coefficient. Okay. Well, since we need to know the different concentrations, right? So KD is equal to the concentration of, well, it's equal to 8.8. And that's equal to the concentration of, I'm going to put caffeine in the organic layer divided by the concentration of caffeine in the aqueous layer. Now they tell us that it's that it starts with 1 milligram of caffeine, right? And so we can think about this as let me do this over here. If the concentration of caffeine, AQ, plus the concentration of caffeine, organic, well, I don't want to use concentrations because they're not the same volume. So if the mass of caffeine in the aqueous layer plus the mass of caffeine in the organic layer have to equal 1 milligram, okay, then if this is X, what's this one? Don't say Y.
One minus X.
There we go. Okay. And it's just 1 because this is 1 milligram. If it were 17, it'd be 17 minus X, right? So then we can plug that in. I did it as the organic was the 1 minus X. That's probably backwards, really. Since we're asked for what the organic one is, I'm going to switch these. Organic is X. Aqueous is 1 minus X. So then the concentration is X divided by our volume, 250 milliliters. And the concentration in the aqueous phase is 1 minus X divided by 100 milliliters. There's no rule that tells us these concentrations have to be in molarity, right? And so milligrams per liter, sure, fine, why not? Okay. So plug away on that a minute. See what you come up with.
With no parking.
Does that mean Ashley got it? I saw Ashley's little dance. Excellent. Okay, so we can figure out how much of our analyte is transferred from one phase to another. Right? This is a liquid-liquid example. We could do exactly the same thing if it was a stationary phase, mobile phase kind of thing, and we knew that distribution constant. Right? But this is an example where you could, this is something that you've done before, right? You've all done separatory funnels. Another useful purpose, another useful way of doing this is to figure out, what volume of organic solvent is necessary if I want to extract 99.9% of my compound, right? You could figure out how much of that organic you would need in order to do that. Okay. All right, so let's move on. When we talk about chromatography in terms of, doing it in an instrument, we have our stationary phase that doesn't move, and then we have our two analytes, in this case A and B. A does not interact very well with the stationary phase. Excuse me. B does interact very well with the stationary phase. And so you can see the direction of motion is top to bottom in this case. KDA is shifted very much so to the mobile phase. KD for B is shifted very much to the stationary phase. And because of that, right, KA is going to come off first in our chromatogram. Right, there's A. B is going to come off later in our chromatogram. And they're going to have obviously different retention times. So when we think about KD, right, a larger KD means an increased retention time, which is T sub R, right, retention time. And a smaller KD is going to mean a smaller retention time. And so that's what this looks like when we do it in an instrument. The term that we use for sort of coming off the column is elution. So there's another term for us to know. So this elution is when our analyte exits the column with the mobile phase. And so A will elute off first, B will elute off second, right? Those are some chromatography specific terms. And then in this particular example, they also had some kind of marker to show us the void volume. Right, this here. It takes the column itself has a certain amount of volume, right? If it's mostly stationary phase with a little bit of mobile phase that runs through it, that little bit of mobile phase that runs through it has some volume, and it's going to take a certain amount of time just for the mobile phase to go from the injection point all the way down to the detector, right? And so that's not really time that the analyte was interacting with the column. That's just time it took to travel through all the tubes and through the pump and down through the detector, and just time that it's spent in the instrument but not really doing any separation. And so the void volume here is that time, right? And so it takes about 1.5 minutes for the sample in this example. It takes about 1.5 minutes for the sample to just go from the starting point of the instrument to the detector. And so to determine void volume, would we choose a compound with a very high KD or a very low KD?
low KD?
Absolutely. We want it to be as low as possible. We don't want it interacting with the stationary phase for a millisecond, right? We want it to be exactly like our mobile phase, but detectable, right? Because we do a background subtraction to subtract out our mobile phase in the detector, we don't ever see mobile phase, thank goodness. And so it's got to be compound with a very low KD. It doesn't interact with the column, with the stationary phase.
Why do we want to know how long that takes? Like, do we subtract that from our...
So if we're good analytical chemists, we do. And we actually report a corrected retention time. And so TR prime is equal to TR. Sorry, I'm going to use little r since our textbook does. TR minus TM, which is this time of the marker, time of the void volume time. Okay. Because columns have different lengths, columns have different, packing efficiencies. We're going to get some variation from column to column, instrument to instrument. However, as long as we're using the same type of column, we should get the same corrected retention time right? This should be the same from experiment to experiment. Whenever we, let's say we had to do some routine maintenance on our instrument, we had to change one of the small capillaries that connects the inlet to the heater, right? Well, if we're going to do that, there's a chance that it might be a millimeter or two longer or a millimeter or two shorter than it was originally. That's going to affect how long it takes something to go through the whole instrument, but it really doesn't affect how long that compound interacts with the column, right? It just affects how long it takes to get to the column. And so because that does affect the retention time, the way that we can correct for that is to subtract out that void volume, subtract out that time it takes to just pass through the instrument unaffected by the stationary. Okay. So looking at this chromatogram, we can also, so in addition to calculating this corrected retention time, we can also look at the retention factor. This is a little k, r. And so this retention factor tells us something about the ratio between the actual volume of the stationary phase inside the column and the volume of the mobile phase inside the column. It's similar to that capacity factor that we talked about in liquid-liquid extraction, because Kr is going to be Kd times this volume of the stationary phase divided by the volume of the mobile phase. And so again, it's hard to talk about concentrations when we're talking about 10 microliters of analyte flowing in a 25 centimeter HPLC column. How do we calculate the concentration? We need concentrations for Kd, but if we know the volume of the mobile phase, that's also called the void volume, right, of a particular column, different from this void volume. I don't know why they called this void volume. It's a time. I don't like that name. So if we know the volume of the mobile phase inside the column and the volume of the stationary phase inside the column, and then again we can look up a KD and relate it to our particular column, our particular instrument. Okay. Our textbook goes a step further and relates VS over VM to VR and calling it the volume ratio. That's I don't know. When you look up a column, when you buy a new column, it comes with a little sheet of paper, and the little sheet of paper tells you, you know, they've analyzed it. It has this much mobile phase volume and this much stationary volume. I don't know that I've ever seen it give you the volume ratio, so why you would include that in an equation, I don't know. First edition of a textbook. What are you going to do? What are you going to do? Right. But what this also does is this retention factor, Kr, we can take that from instrument to instrument to instrument, right? For a given compound and the same type of column, right? We can also change column types, but for the same type of column, for the same solvent system and the same analyte, we can look up a KD and we can, if we know that those two volumes, then we can calculate Kr. And that Kr we can take from instrument to instrument to instrument, and it should be the same for a given element. So a lot of times when you look at chromatography papers, while they will report KD, the thing that they really compare are those retention factors, KR. There are times when we don't know necessarily the volume of the stationary phase and the mobile phase. And so what you can do is you can do an approximation based on retention times. And to do that approximation, right, Kr is equal to the amount of time that the analyte spent on the stationary phase. And so that's going to be our retention time minus our marker time, right? That's our corrected retention time, Tr prime, divided by the amount of time that just the mobile phase spent on the stationary phase, right? And again, that's our marker time, Tr prime over Tm gives us our Kr. Right? And so this is a decent approximation, and it's one that lots of folks use. Just like KCF, right? This can tell us something about the separation efficiency. And so, you know, either one of those equations for Kr, if you have the chromatogram in front of you, you can calculate it using the corrected retention time. If you don't, and you're trying to figure out what it would be, you can look up some data on your column and figure out the stationary volume and the mobile volume and figure out Kr that way. Okay. All right. So this selectivity factor, let's talk about it a little bit before we do an example. The selectivity factor is a way for us to compare two different analytes, and it's equal to this retention factor, I'm going to say prime over retention factor double prime, with the knowledge that Kr prime is for the less strongly held analyte, and Kr double prime is for the more strongly held. Wait a minute. That can't be right. Alpha is always greater than 1. Yeah. Alpha should always be greater than 1. So I have my more and my less backwards. I apologize. I apologize. Yeah. Okay. And so what this tells us, what alpha gives us, this selectivity factor, selectivity, if you remember from exam 1, is the ability to analyze only one component out of a mixture. Right? And so this selectivity factor tells us a little bit about how well resolved 2 components are going to be. Right? And so this gives us some information about how easily 2 components can be separated. And so go ahead and calculate alpha, sorry, for this example. Did you get that? Excellent. Right. I cut out an algebra step, right? Kr prime and Kr double prime are both divided by Tm. Right? If it's in the denominator for both of them, then it cancels out. Okay. And so again, if it's a alpha of 1, that essentially means they are exactly the same thing, right? And not very separable. As alpha increases, They're more separated in time, more easy to resolve. Our method is more selective. Okay. All right, we'll start talking about resolution on Friday. I hope you have a great Wednesday.
I thank you.
Hello.
Hey, Dr. Davis.
Hey, Ashley.
Can we talk to you about our lab, the quad chart? Is that due Friday still?
It is ideally.